Thank you for the introduction. And thank you guys all for attending both in person and online. Today I'll be talking about, or I'll go ahead and read the title, The Effects of SOFC or Solid Oxide Fuel Cell Pressurization and Investigation of Solid Oxide Fuel Cell Gas Turbine Hybrids for Aerospace Applications. So that's not a mouthful at all. Quick agenda, just kind of high level. We'll start with the motivation for kind of why a more electrified aviation is beneficial. Then kind of give a roadmap for kind of laying out some of the work I did and giving some kind of explanations for that. And then really dive into the details of solid oxide fuel cells and solid oxide fuel cell hybrids and a lot of the work I did there, which is kind of following the roadmap, and then we'll end with the summary. So quick motivation. If you think of like a battery hybrid or an electrochemical kind of hybrid engine, you compare that to an internal combustion engine, the hybrid is going to be a lot more fuel economic. Think of like a Prius having a lot more miles per gallon than a Mustang. So this kind of technology that you've seen, employed in the automotive industry can kind of be employed at the aviation level as well. And what you end up with is just kind of this high efficiency power generation method. And that high efficiency does two things for you. It helps environmentally, because if you're at a higher efficiency, it means you're burning less fuel. So you're going to emit less carbon dioxide. Estimations, when you kind of compare the system I'll be talking about today compared to a LEAP 1B, which is the engine on the 737, can decrease carbon emissions by about 60%. This high efficiency that these SOFC hybrids can achieve will essentially kind of cut the existing fuel burn in half. So when you look at an airline's total operational cost, around 17 to 30% of that comes from fuel. So if you're cutting your fuel burn in half for the same kind of power output, that's going to significantly save you a good amount of dollars there. So both the economic and environmental motivations are why like a more efficient, a more electrified aviation is kind of wanted. So we have kind of a rough motivation for why electric aviation can be good environmentally and economically. So I want to kind of go through this roadmap, and I'll try to use the laser pointer as a guide. So starting in the up top right here, I have like pictures of these future concepts for more electrified aircraft. And they all have their own different kind of mission profiles, their own applications. But what they all have in common is they need a source of electrical power, and ideally a high efficiency electrical power. So that's where this first arrow is. What I'm proposing to power these future aircraft is this SOFC combustor turbo generator hybrid power plant. This power plant is great. It has environmental and economic benefits that I mentioned previously, but it has some caveats and unknowns that I wanted to look at deeper kind of in this dissertation. So that kind of leads you on this first path to number one, where the fuel cell component in this hybrid system is required to operate at elevated pressures. So anywhere between 3 and 20 times atmospheric pressure. And this is kind of scarce in literature, especially for tubular SOFCs, which is the geometry kind of fuel cells I'll be talking about today. So the first step in the roadmap was to kind of get a test stand so we could get data for these fuel cells in similar conditions to how they would be operating kind of in this larger power plant. So we kind of have a database of these fuel cell performance data in similar conditions to the power plant. And you can use that database along with kind of a theoretical model of the fuel cell to actually fit this kind of numerical model that's capturing the gas diffusion physics, the electrochemistry that's happening inside the fuel cell. You can fit that using the data, and that allows you to kind of learn a lot more about what's happening inside the fuel cell, because with the model you can kind of delineate certain contributing factors. And this model is great. And it's really good for if you're trying to, optimize the performance of a fuel cell, but it can be computationally expensive, especially if you get to higher and higher fidelity models. So when you're trying to evaluate the performance of this kind of hybrid system, you want something that's really rapid and quick. So using this kind of complex model that is representative of data, this can be simplified down to I'm calling like a reduced order surrogate model that's able to capture the performance of the fuel cell and how that changes with different operating conditions in a very rapid way. It's kind of just a single algebraic expression compared to multiple different functions and numerical solvers that are required to do the more complex SOFC fuel cell modeling. So then we kind of go back to the beginning here. Another caveat unknown of this system that I want to look at is that it's going to be heavy. So depending on how it's sized, a solid oxide fuel cell system compared to an existing technology, internal combustion engine gas turbine, is maybe around 2 times heavier. And when you're looking at aircraft applications, this mass is very important. You want to try to minimize that as much as possible. So when you're trying to calculate the mass of something, there we go. Got it. Nice. When you're trying to calculate the mass of something, it's helpful to know how it's put together. So that's kind of what this step 4 is. We came up with the strategy of how you might put together, actually build this SOFC combustor hybrid. And you actually end up with this kind of interesting problem that you can do some optimization on, allowing you to kind of minimize the mass. And then these two kind of rapid tools that are capturing these more complex effects can be combined to this final kind of step in the roadmap where this plot means nothing to you, but to the trained eye, it can be used to kind of size an SOFC system for a given application. So using these tools for the fuel cell and the mass modeling, along with kind of a thermodynamic model of the system, you can kind of use these tools to help you optimally size this SOFC hybrid system for an aircraft. So I know that was a lot. Oh, let me move my mouse here. But we'll kind of just give an introduction on what this SOFC kind of gas turbine hybrid is. So this plot here shows on the x-axis kind of plant size, and on the y-axis electrical efficiency, and it's comparing a bunch of different power generating technologies. You have your internal combustion engines that are in your car, gas turbines, both small and large scale, and when you have this kind of pink parallelogram that is representing this SOFC gas turbine hybrid, and it's the highest efficiency in class. So that's why these systems are so attractive, is they can achieve very high efficiencies when compared to a wide range of different power generating technologies. So a big component of this is the fuel cell. So for those who don't know, I'll just kind of quickly go through what a fuel cell is and some of the benefits. But a fuel cell is an electrical energy conversion device, an electrochemical energy conversion device, very similar to a battery. But unlike a battery, it does not store its chemicals in its housing. You flow these chemicals. So it's primarily made up of 3 layers. It's called a cathode, electrolyte, and anode. And what you do on the cathode is you flow an oxidizer, which is normally air, the oxygen in the air. This oxygen diffuses through this porous media, which is this layer, this cathode layer. On the fuel cell, it gets ionized. This ion is transported through the electrolyte where it meets a hydrogen molecule. And then this kind of ion electron that is used to ionize the oxygen is sent through this external load. So with this transport of the electron, you're actually able to generate electricity. So some differences between solid oxide fuel cells and other fuel cells that you may have heard of is that SOFCs operate at very high temperatures, anywhere between 600 to 1,000 degrees C, depending on the materials you're working with. So that has some downsides, but it also has some really good upsides when you look to try to combine the system with this gas turbine power plant. And then lastly, there's 2 main kind of geometrical forms of these SOFCs, these solid oxide fuel cells, and one of them being tubular and planar, and I'll be talking about pretty much just the tubular ones today. So when you want to hybridize the SOFC with the system, you end up with kind of a thermodynamic cycle that's looked like this. And this SOFC gas turbine hybrid is not like a novel technology that I'm introducing out to the world. It exists, and it actually has been demonstrated. You can see some of the some of the existing demonstration, or not even demonstrations, existing products that kind of implement this SOFC gas turbine hybrid technology. So as I mentioned before, the fuel cell operates at really high temperatures. It's like 600, 800 C. We operate with ones at 750. And in a pure fuel cell power generating system, its exhaust is just going to be carrying away this useful heat, this useful work. So what loves to take advantage of kind of waste heat? A turbine, a gas turbine. So this fuel cell has hot exhaust, and it's now being sent to this turbine, which is able to do 2 things for it. It's able to make more electrical power, as well as power the compressor, which is connected to the shaft, supplying the fuel cell with the source of air. So it's this really synergistic interaction between the 2 components, why these systems can achieve very high efficiencies. But a caveat to kind of these ground-based systems is that they don't have to deal with a whole lot of transients. Maybe just on startup and shutdown, they're having to deal with kind of some load transients. But in an aircraft, the amount of power required is changing vastly. Think of, a takeoff going from 0 to 37,000 feet, really vast changes in ambient conditions, as well as kind of how much power you need. So these systems are not quite equipped to handle that. So in order to have this SOFC hybrid system be more equipped to handle the dynamics, we've kind of made a modification to the system. So now, instead of just calling it the SOFC gas turbine hybrid system, we're now calling it the SOFC combustor gas turbine hybrid system. So what this did is it kind of removed this heat exchanger right here. This heat exchanger was responsible for thermally managing the stack. It took the fuel cell stack. It takes the hot turbine exhaust through a heat exchanger and heats up, the incoming compressor discharge. That's a very slow process, especially because this heat exchanger is really large thermal mass. It also adds just a large mass in general. So when you're kind of looking for aviation applications, it's maybe not too good. So the thermal management of the SOFC has now been replaced by this kind of anode off gas combustion process. So it removes kind of the needed high temperature valves, as well as the heavy, both thermal time constant and just heavy in general heat exchanger, and replaces all of that dynamics with kind of just a fuel valve and modulation of how much excess fuel is leaving the fuel cell and sent to this combustor. So we've done studies with the system, in a dynamic environment using MATLAB simulating transient models, and we've been able to kind of verify that a system like this could possibly work for a very large scale kind of 737 class fully electric aircraft. But this hybrid system has some implications. I alluded to previously. It requires pressurized operation of the fuel cell, which is not something that's super readily available in literature. But also, the dynamic, the SOFC system that's going to be operating in an aircraft has changes in its gas compositions on both the fuel and air side, as well as changes in electrical load. So we need data that's kind of capturing how the fuel cell behaves in all of these kind of changing environments. So that leads us to kind of the next part on the roadmap here. Step 1, where I'll talk about kind of the data that we got and how we got that data. Before diving into that, I kind of want to give just a quick background on the kind of data that we're getting. So this is a VI, a voltage current, or a polarization curve. They have kind of those couple names, but they all mean the same thing. What it shows you here on the x-axis is the current, so how much electrical load you're trying to draw from the fuel cell. And then on the left y-axis here, you have this blue line, which represents the cell voltage. How much power you make is voltage times current. So that leaves you with this parabolic power curve. So when you test these fuel cells and generate these polarization curves, you kind of get like an operating line. If you need to produce, this much power, okay, now we have to be at this load, and we're going to be at this voltage. So it tells you a lot about how the fuel cell behaves under kind of a changing load environment. There's these two main points. There's a peak power point where you're maxing out your power before all these losses become too dominant. And there's the peak efficiency point, which is at a much higher voltage, but much lower power rating. So some things to kind of keep in mind, because the curves that we make, look very similar to this. Before talking about the data we gathered, I wanted to briefly talk about some of the stuff that's out there in literature. So referring to tubular SOFCs, there's really only two groups out there that I've seen published data about. The first one being from Japan. They test these very interesting kind of microtubular SOFCs. So the ones that I work with are a foot long, and half an inch in diameter. These are a couple millimeters in diameter, so very small, kind of like straws. But what they see is when you increase the operating pressure, you get an increased performance. So that's a good sign. So if these SOFC hybrid systems need to operate at higher pressures, you're going to get better performance out of this fuel cell, which that's good. And that same phenomenon was observed by another group in China. They were testing kind of a different structure. It had a closed end, which kind of changes the flow paths and some of the flow characteristics. But again, when they increase pressure, they're seeing an increase in performance. So these are really the only two. So literature is kind of scarce with regards to tubular SOFC pressurization. So that's why we built this test rig, which you can see here. So and I'm not going to, I wish I could probably speak an hour on this test rig alone, but, I'll give it one slide here where you have this pressure vessel. It houses internal heaters. It has mass flow controllers to allow for controlling, gas compositions, what you're feeding it, as well as, load cells to control, how much power you're drawing from the SOFC. You can see an example fuel cell shown here on the left. It's about 1 foot long, an inch and a, or a centimeter and a half in diameter. Sorry for switching up units so much, but it's a good time to mention all the fuel cells that I'll be talking about today were provided by Special Power Sources. They're a fuel cell manufacturing company out of Alliance, Ohio. We Tennessee Tech partners with them on multiple different fuel cell application-based projects funded by the government. So very gracious to them for supplying the SOFCs needed for this work. So here you can see kind of all the polarization curves we tested. I know it's a lot, but what you're looking for is these power curves. As you increase in pressure, you're seeing an increase in power. So that's good. We're seeing pretty similar behavior to what we measure in literature. The exact amount of performance increase you get due to pressure is going to be dependent on kind of the materials the SOFC are using, the geometrical constraints, how thick it is, which is kind of the reason why we have separated this into 3 batches, because the key differences between these 3 is kind of how thick your anode layer is. All of these curves were tested with hydrogen as the fuel, pure hydrogen as the fuel on the anode, and air as the oxidizer, using oxygen, just the 21% that's in the air. We also ran some of the cells on methane, where you can still see a performance gain increase due to pressurization, but you'll see around maybe a 13 to 18% lower performance due to hydrogen, or compared to hydrogen. And that's just because when you have methane, you're actually going to have a lower kind of partial pressure of hydrogen, increasing your losses. One phenomenon that was kind of unexpected that, to the trained eye, you definitely would have seen this and questioned it, is this: we actually measured lower performance at higher pressures for some of the VIs. Now, we hypothesize this to be due to fuel leakage. The reason I think that's the case is you can see this fitting up here on the top right. So when we would test a fuel cell before it's kind of been loaded, pressurized, heated up, we would load it into the test stand and run a leak test, where we flow a mixture of 5% hydrogen and 95% nitrogen through it, and then kind of use a handheld hydrogen detector to sniff the line for leaks and sniff the fuel cell for leaks. And before a test, we would not really measure any kind of leakage here at this fitting. But this fitting is very crucial. It does 2 things. It kind of electrically isolates the fuel cell, but it also kind of seals the fuel flow from the airflow. And when this paste here gets thermally cycled, it can crack. Or at least that's what kind of this whole hypothesis is based on. And fuel can leak out of it, dropping the performance. So you actually see, as you go up in higher pressure, you measure the lowest performance, but then there's this kind of turning point where now pressure begins to have a good effect and increase your overall measured power. And when you kind of take a more theoretical and modeling approach to this, you can use techniques that are pretty widely used in like the natural gas pipeline industry, because they have these small like pinhole cracks. So it's modeling kind of a similar phenomenon. And when you kind of evaluate that in the case of an SOFC, you get some results that really make sense why you see this kind of crossover point. So if you're leaking out of this crack, it's a constant volume of leakage. But when you're actually running this VI curve, what you're doing is you're steadily increasing the mass flow of fuel, because you're kind of wanting to maintain a constant utilization. So when you do that, the percentage of flow that's leaking actually becomes less significant, which is what this y-axis on the left here is showing. So as you go up to higher currents, as you go further along this VI curve, this leak fraction, the percentage of flow that's leaking, becomes less and less significant. So the effects of pressure begin to outweigh kind of this effect of leakage. So kind of getting back to quantifying the performance increase due to pressure, you can generate these plots, which we'll look at the top 2 first. What they show on the y-axis is a power normalized to 100 kilopascals. So if you were at 400 kilopascals, which is for 4 times atmospheric pressure. You would take the power measured there and divide it by the power at 1 bar. So it's just really nice number that allows you to easily kind of calculate percentage changes. So this top graph is showing different constant current lines. So on this polarization curve, we're kind of drawing a vertical line here and then calculating this normalized power. And what you see is as you go up and increasing current loads, so you go from lower to higher loads, you see a higher sensitivity to pressure. This is likely due to the actual voltage losses, what's governing the level the voltage at for a given current. As you go up to higher currents, these losses, the magnitude gets higher. So now this pressure term is affecting this kind of larger magnitude loss, which is why you kind of see this increase in performance, an increased sensitivity to pressure at higher currents. You can do the same thing at constant voltage line, and what you see is now you have like a 50% increase instead of a 20 to 25% increase. And that's not just like magically, okay, now your performance gets so much better. It's just really how you're kind of referencing this performance increase. When you do a constant voltage line, what you care about for your delta power is the change in current. When you do a constant current line, what you care about for kind of how much this power is improving is the change in voltage. And the change in current is going to be larger than the change in voltage, which is why you see such a larger magnitude for this normalized power. But, so we did a lot of testing. We got a lot of useful performance data with all these different fuel cells. So now I'll kind of talk about some of the theoretical modeling of the fuel cell and then how we use that, gathered data to then fit the model to what we measured. So I've showed a lot of polarization curves already. Excuse me. And what this polarization curve does a really good job of kind of laying out the different electrochemical losses or phenomena that are occurring that kind of govern the shape of this polarization curve. I'm not going to dive into it. That could be its own couple-hour lecture. But what's important about these is the highlighted terms. So there's all these P terms, and what they are is they're local partial pressures. So when you're have a model that's calculating the performance of the fuel cell, this is where the effective pressure is considered in these local partial pressure terms. And this is why when you increase pressure, you see an increase in performance. It's because the magnitude of these partial pressures is getting larger, dropping kind of how much voltage loss are from each different kind of loss mechanism. Oh, wrong way. But how do you get these partial pressures? Because what these partial pressures represent is kind of a concentration of a gas molecule you care about at the actual location, like where these electrochemical reactions are happening. So that you use a diffusion model to kind of help you calculate that, help you calculate how these gas species are diffusing through the porous media that is kind of the electrode layers of the fuel cell, and then allow you to kind of feed those back into the loss terms. So the main one I want to kind of focus on here is called Fick's law, which is very familiar if you guys are familiar with diffusion. It's the kind of the basic, most simplistic law. It just assumes that whatever concentration of species you care about as it diffuses through, or is the concentration of that species you care about is directly proportional to your depth and kind of that electrode. So it's just the solution to this differential equation ends up just being this expression here, which is just a linear expression. Then you kind of have these more complex models, such as the Stefan-Maxwell model. The most widely accepted diffusion model in SOFC literature is called the dusty gas model. And I kind of have these pictures here, which are showing, some of the key assumptions and differences, but, they start to consider the actual intermolecular collisions. They're actually considering kind of this diffusion through this static species, which is kind of representing this porous media. But the model itself is much more complex. You can kind of see an example of one of the formulations here. So this requires some sort of numerical solution, unless you're smarter than me and can solve it by hand, compared to this one, which is very straightforward to analyze. So when I set off on this work, I wasn't sure which diffusion model I was going to choose. I wanted to choose, the most accurate one. But what I found is that is pretty interesting. And these plots show what I'm about to talk about. On the y-axis, it shows kind of this volume fraction of the species we care about for the fuel cell reactions. And then each different line represents a different diffusion model that I tested. The most important, or the most simplistic one is Fick's law, which is kind of highlighted here, shown in the red squares. And what you see for both oxygen concentration and hydrogen concentration, Fick's law does very well at matching kind of these more complex models. So the more complex models that you kind of want to use as the standard are these green triangles, black diamonds, and magenta upwards triangles. So we see that, Fick's law is right on line with kind of what they're predicting. And it's even covered on the hydrogen side. You can't even see it. It's kind of agreeing with these more complex models. And it's able to do this kind of how you're adjusting this term here. If this diffusion coefficient is considering kind of these more complex diffusion mechanisms, then you can really kind of get away with using a much more simple expression. Just to reiterate, kind of these diffusion models are calculating the partial pressure or concentration of a species you care about kind of within this active layer. This is where the actual kind of all the reactions are happening. We're at this triple phase boundary, what people tend to call it. So this is the location that the diffusion model is actually helping kind of solve. So, with that, I was able to say, okay, Fick's law, it's simple, but it's, pretty accurate. And I did a lot more comparisons than what just was shown there. But now we kind of need some data. The data kind of showing the diffusion behavior of the cell. So that's what all these surfaces are here. They show on the x-axis a variation in kind of feed oxygen percentage, and on the y-axis a variation in the feed of hydrogen percentage, which is kind of analogous to how these things might change in an actual system. And then for each variation of those two feed compositions, we increased the pressure as well as changed how much current we're drawing. You see some pretty interesting behavior. The y-axis here shows this kind of normalized power. You can think of it just as a power. A bigger number means more power. And what you see is there's actually a higher sensitivity to the change in oxygen mole fraction compared to the change in hydrogen, even though they were changed to very similar scales in reference to their nominal value. So that may lead you to believe that maybe the cathode side, the air side, is much more dominant in the loss. But you can't really directly make those conclusions just from this data, but it is test data that you can use to fit your models to, which then you can dive into the models to really see that. And as I mentioned, or hopefully I mentioned previously, kind of this diffusion model is where the effective pressure is really taking effect and kind of the prediction of performance. And it's where changes in the gas composition is considered within trying to calculate the performance. So this diffusion model is really the key for getting a successful SOFC model. So here you can kind of see some of the fits that we did. On the left, the experimental data is shown in the data points, and then the fit to that data is shown in the solid line. So very good fits, I would say, where this model is pretty representative of what we measured. And then again on the right, where we have at these higher current densities, very good fit to the model, except at this kind of lower current density zone. So these data points were actually left out of kind of the fitting algorithm. Because I believe that they were influenced by this fuel leakage phenomenon. So I didn't want to kind of bias the model with that. And then what you actually see, what the model predicts without considering fuel leakage, is higher performance than what we measured. So that maybe is helping this kind of leakage hypothesis to it may be kind of the true thing, or what is actually happening. And then when you kind of repeat those surfaces where you're varying the gas composition with the model, you see very good agreement after you've gone through kind of this fitting process, where the blue surfaces show the model prediction, and then the red surfaces are showing the measured data. And then most time these are overlapping. They're very good agreement. Excuse me. And this along with kind of the fits to the polarization curve led us to believe that the model is truly representative, or is pretty representative of what we've measured, allowing you kind of to get up and run with the model to try to learn more things about what you measured. So that's what these charts are showing. So the experiment was repeated, where we're varying kind of this feed percentage of oxygen and the pressure, and as well as feed percentage of hydrogen and the pressure. But now these two surfaces are directly separating what loss is coming from the cathode and what loss is coming from the anode. So these two kinds of sides of the fuel cell. And what you can see is that in almost all instances of these two surfaces, the cathode is the dominating loss. So this is pretty useful information for if you're an SOFC manufacturer trying to improve the performance. Using this kind of model fitting technique, you can dive in and see, okay, this is how much performance we can actually gain by adjusting this layer. And then, the anode side, this red surface doesn't become dominant until you get to, exceedingly low hydrogen percentages, as well as kind of lower pressures below 1.4 bar. Then the anode starts to become more dominant. But you could rerun this kind of experiment for, the exact ranges of compositions you expect to see, and that'll allow you to kind of know, okay, maybe if we want higher performance, we need to, take this route in improving the cell. I think I'm doing okay on time. But kind of back to the roadmap, we'll go to the next step in this kind of fuel cell exploration path. And it's taking that kind of complex model that we use to, match the experimental data, but it's more computationally expensive, and we really want some sort of rapid tool that can estimate the fuel cell performance without having to, run all these numerical solvers. So the first step in kind of this reduced order model is this normalization technique. So what you see on this left chart is all the power curves from the different fuel cells we tested. And there's really large variation in these curves. Low performance around 0.3 all the way up to high performance around 0.6. But when you normalize them, so the way you normalize them is you divide kind of their actual power at each point by this peak condition. So the power maybe at this point, kind of the furthest point along the curve where you have this peak power. And that gives you this chart on the right, where now you have, the variation and the different shapes of the curves goes away, and they all kind of collapse onto one curve. What this tells you is that, the relative, voltage, current, or power versus current behavior of the measured fuel cells is the same. What's changing is just the slope of this kind of voltage drop. So this allows you to kind of just have one expression to kind of represent the general shape of the curve. And then you can scale that expression. So that's what was done here. So this was actual data, voltage in the blue and power in the red. Then you normalize it by its peak conditions, which were around 1.3 amps per centimeter squared, and you end up with this normalized curve on the right. So the normalized power is going from 0 to 1. Normalized current is pretty much going from 0 to 1. And then this is an expression that can be easily fit by a quadratic expression, which you can see here. And then with this single expression, along with these kind of normalization equations and techniques on the right, you can generate this chart on the bottom left, where now with a single expression, you have estimations for the fuel cell performance if it was a low performing fuel cell or all the way up to a high performing fuel cell. And you're just kind of assuming that, this relative voltage, this polarization behavior is staying constant between these cells, which, is not too bad of an assumption, because, this is actual measured data, and a lot of these curves end up looking the same, just kind of scaled. But that expression can get even more kind of robust and, and useful. So since we've kind of normalized it by a peak power condition, you can track how the peak power is changing with respect to different operating variables, like the pressure, temperature, fuel and oxygen site compositions, as well as some other variables. And now you can, reference that to some sort of datum and track how this peak power is changing at higher temperatures or lower pressures or whatnot. An example is shown here. So this is very simple. It's just pressure on the x-axis and kind of your percent performance increase on the y. So you could fit an expression to this, and now you can combine it with the polarization model. And now you have a VI curve that's sensitive to pressure, and it's just one simple equation. So that's kind of what I did, but I used the electrochemical model to kind of explore how the performance changed with respect to these changing operating conditions. So I was sure that the electrochemical model was kind of matching the experimental data. And then I could just kind of went to town and play with the electrochemical model. And now you end up with kind of this added expression here, which allows you to kind of track how this peak power is changing with respect to changes in pressure and fuel utilization. So with this single expression here, now you can generate a chart like this on the right. where you have kind of a low performing fuel cell, a high performing fuel cell, and then how it would change when you change fuel utilization or pressure. So that's a pretty robust tool. And now instead of having to model, I'll quickly go back to it. All of these expressions, the complex diffusion model, you get rid of that and just it's all one expression now. Where it's still kind of, and it's all based on measured data. And that is where this all comes from. That's kind of its father. And these models can get even more complex, but you still end up with just kind of an algebraic expression. This one looks a little gross, but I had success fitting, these reduced order models up to 5 different parameters, and still maintained a pretty good accuracy when comparing the reduced order model to kind of the fitted electrochemical model. So these things can be pretty powerful. So kind of we have this, reduced order model tool, this rapid evaluator of fuel cell performance now. Now going back to kind of the other question I wanted to look at, which was that these systems are heavy. So to start with kind of talking about the mass of these systems, I wanted to go over kind of the strategy that we use to put it together, because that's really how you're kind of calculating the mass. So starting here in the top left, we just start with our building blocks, these fuel cell tubes. These tubes then get packaged into this SOFC combustor submodule. So each of these submodules has their own thermal management and exhaust capabilities. And then depending on your power needs, you can kind of stack these modules in this pressure vessel here. And this pressure vessel does 2 things. It seals, the overall, and is holding the majority of the pressure, as well as if you can get clever about kind of where you put the boxes, you can actually get some manifolding. But through this vessel can do some manifolding for you. But the fuel cells are hot, and this pressure vessel is likely going to be some sort of metal. So there is an insulation layer between these boxes and the pressure vessel to ensure that the yield strength doesn't degrade too much. And depending on your power needs, you need a bunch of these vessels, or maybe you just need one. And then those kind of get hybrid or get integrated with this gas turbine technology before being placed into an aircraft. But we know how, so we kind of defined how it's being put together. So to actually calculate the mass, you need kind of this couple geometrical stress that's capturing kind of the hoop stresses and the different stresses of the pressure vessel. And then there's also like thermal considerations, because the fuel cell itself is hot, and the yield strength of these metallic pressure vessels is going to be directly related to temperature. So you get this kind of interesting problem where you can change this thickness of insulation. You can change how these tubes are packed within these submodule boxes, and it allows you to kind of let an optimization algorithm just run with it. You can change these variables, and you can constrain, what this optimization algorithm can do and how it can change the variables. But now, you can evaluate this kind of model for any sized SOFC. So say you need, a very small kind of, you don't need that much power. You can put that into this model and then kind of use an optimization algorithm to minimize the mass, so that you're getting the most bang for your buck. You're getting the most power dense kind of SOFC combustor system. So kind of in a similar method to how the fuel cell reduced order models were made, the same thing was done for this kind of mass model. So on the top right, here are the independent variables. The first one being active area, which is like almost directly analogous with kind of your SOFC power rating. So this reduced order model is sensitive to like how big your SOFC is. So maybe you have 10 megawatts, or maybe you need 100 kilowatts. So very small and a very large range. It's also sensitive to pressure ratio. So what's your gas turbine operating at? Because that's going to directly affect kind of the hoop stresses of this pressure vessel. And then the last 2 things it's sensitive to is kind of the individual tube geometry. It's actually pretty interesting when you kind of run these, when you run variations in these independent variables, you see that an ideal system wants to have the longest tube and the smallest diameter tube possible. And that's going to allow you to have the smallest mass. And we can dive into that later if people have questions. But so maybe those microtubular guys in Japan were onto something with the small diameter tubes. But you can see the performance of this reduced order model here. It's pretty well, or I thought it was satisfactory, staying within plus or minus 10% of the actual predicted mass, and then plus or minus 5% of the predicted volume. So, we've gone through the majority of this roadmap here, where we have this kind of rapid tool to evaluate the fuel cell performance, and this rapid tool to evaluate, the mass of the system. and optimize and minimize mass. Now we want to kind of use those tools to see how this integrated system is going to perform and actually kind of make these maps that help us size the system. So this is the system diagram that I'm going to try to apply to 4 different aircrafts. But the main takeaway is that kind of this whole thing that I'm circling with my laser pointer is the power generation side. Then the propulsion side is handled by taking power from the fuel cell, taking power from the generator that's attached to the gas turbine, and handling it in some power electronics, and then spinning a motor. And that motor could be spinning a propeller, a ducted fan, a bunch of them, or just a couple of them. It doesn't really matter because I'm more so focused on kind of just generating the power. One special thing about this system and a method that I use to actually kind of size the system is this combustor here highlighted in yellow. So we call this kind of a post-combustor or a supplemental combustor. And what it allows you to do is drastically increase like the power output of this system at a given operating point. So say at takeoff, you have a very high peak power demand, or maybe at top of climb, you have a very high peak power demand. So what you can do, instead of just operating off kind of the waste heat of the fuel cell, which I briefly mentioned earlier, now you can add supplemental heat through the addition of more fuel and combustion. So now your turbine can be, ramp up its power significantly by utilizing kind of this added heat. And this is another knob you can turn when trying to size, how big your gas turbine is, how big your fuel cell is, and it is pretty useful when determining a system or trying to find a system for a specific application. So I looked at 4 aircraft. Here's kind of just a big table summary of them. But the first 2 were NASA urban air mobility concepts. So these are kind of short hops. They only go up to 10,000 feet, and they carry like 6 to 10 passengers. So much smaller scale. And then the other 2 aircraft I considered were kind of Boeing 737 single aisle aircraft kind of replacement. So the first one is another NASA concept called Susan. It's kind of a really innovative take on the single aisle aircraft. It's including a lot of different new technologies. And the last aircraft is a kind of this hypothetical fully electric Boeing 737. But what's really important about these and what ultimately is influencing how you size the system is these power requirements. So at takeoff, the UAMs need about 1 megawatt of power and then a reduced power at cruise. The single aisle aircraft need a much more substantial power because they're a lot larger. And then they all have their design takeoff and cruise altitudes, speeds, and then a mass constraint, which is shown in this column. So all of these are really influential when trying to size the system. So here's kind of my approach. So you have these aircraft, you know how much power it needs at takeoff, you know how much power it needs at cruise, kind of its other constraints. So how do you actually pick how much power from the fuel cell, how much power from the turbine? So I started at takeoff. So at takeoff, I enforce this constraint that every possible system I look at has to make the power that the aircraft needs at takeoff. So that's 1 megawatt for the UAM, the urban air mobility concepts, or 30 megawatts for this fully electric Boeing 737. And then you vary these 2 parameters. And when you vary these 2 parameters, what this kind of thermodynamic model of the system is doing is it's changing your sizes of your fuel cell, and it's changing your size of your gas turbine in terms of how much mass flow it has. So this first one is turbine inlet temperature. So let's kind of just give an example here. So I'll introduce the other one first. The other variable is the percentage of that peak power that's coming from the fuel cell. So for the UAM case, we have 1 megawatt power demand. Say 50% of that is coming from the fuel cell. So that means the other 50% needs to come from, the gas turbine. Now, if you have a very high turbine inlet temperature, a lot of the power from the gas turbine is not coming from that, supplemental heat addition. Whereas if you have a very low, and so what that kind of leads the system and the model to do is to get a mass flow of the gas turbine that's really low. Now, because that's where your power is just coming from the supplemental heat, not the mass flow. And then kind of vice versa of that, you can go to very low turbine inlet temperatures, and now the mass flow of your gas turbine has to get really big because that's where the power is coming from now. It's not coming from this heat addition. So when you vary these two things, in set ranges, you now end up with a bunch of different combinations of gas turbine mass flow, so how big your gas turbine is, and how big your fuel cell stack is, which is what this kind of chart shows. So on the x-axis, you vary kind of the turbine inlet temperature. On the y-axis, you have this percent power from the fuel cell. And this chart on the left is showing kind of a contour of what this model is solving for, kind of the size of your gas turbine. And what you see is as you go up to really high turbine inlet temperatures, you have a lower mass flow because all that power is coming from that heat addition and then not the mass flow. And then if you go up to higher and higher percentages of fuel cell, your gas turbine can get smaller because now more of that power comes from the fuel cell and it doesn't have to come from the turbine. And then on the right, you're just kind of showing that the number of tubes, which is directly analogous to kind of how big your stack is, its power level. And it has no correlation with turbine inlet temperature. It only changes with kind of how you've specified the percent power that's coming from it. So every point on these two charts work for the takeoff condition. They all will satisfy your 1 megawatts on the ground, your 30 megawatts on the ground, depending on what kind of application you're looking at. Well, I want to know which of these systems also works at cruise. So to do that, you kind of have to, or I made some simplifying assumptions to kind of allow for rapid and very wide design space search. So you take each system that works on the ground and you bring it up to altitude. So for the UAMs, go from 4,000 to 10,000 feet. And and then the next thing you do, which is kind of a user assumption, is I shut off that supplemental combustion. So what that did is it kind of increases. Maybe I'll close this window. We got a motorcycle going crazy outside. Thank you for bearing with me. So when I shut off this kind of supplemental fuel flow to the combustor at cruise, what this is doing is it's kind of lowering your overall power generation. So you're not going to make as much power because you're not giving it, the gas turbine more heat, but it leads you to kind of a more efficient region because now the majority of your power could be coming from the fuel cell instead of this kind of more inefficient gas turbine. The next thing you do is you kind of scale the mass flow. So when you go from 0 to 37,000 feet, there's vast changes in the ambient air density. So which gets much lower at 37,000 feet than it is on the ground. So you need to properly kind of scale your design mass flow of the gas turbine with that using this kind of expression. And then you evaluate how these systems perform at cruise. And you end up with this kind of resulting cruise design space. So here's an example of this where every point on this chart makes your 1 megawatt on the ground or at your takeoff condition. And now you have these constant power contour lines of how they're performing at cruise. So say your aircraft needs a megawatt on the ground and 500 kilowatts in the sky. So you'd be on this line. So every combination of gas turbine and fuel cells, or a gas turbine mass flow and kind of fuel cell stack size that's on that constant power contour line is a system that could work for you or work for that kind of application. Just a couple, like the mass flow does degrade significantly. Just from going from 4,000 to 10,000 feet, you see like a 25% drop in mass flow, but going from 0 to close to 40,000 feet, you see around a 75% drop in mass flow. So that really does kind of influence how you choose your system. So now you can kind of take those contours that I just showed on the last slide and plot some other things on it. So you can plot maybe an objective that you're trying to optimize. You can plot some constraints. So that's kind of what I've done here with these two example plots. So you can still see the constant power contour lines shown in black on both of these plots. And then the two NASA urban air mobility concepts, what they require at cruise, kind of shown in these magenta lines. So say your goal was to maximize efficiency, which is this kind of blue contour. So you're trying to make that number as big as possible. So for one of the UAM concepts, you're trying to push this line as far as you can out to the right to maximize your efficiency. But maybe you're trying to maximize range. So that's what this part is here on the right, where now you see this blue contour removed efficiency, and now we're adding range. So to get the most range, you need the most power dense system is kind of what this is telling you. So you don't want as much fuel cell at all, and you need to have a very power dense gas turbine as well, and that's going to give you your kind of maximum range. But you can also see that you can still end up with kind of a very efficient system, 40, 50%, and still get the majority of your range. But you end up with, a lot more significant fuel burn. So there's a lot of these kind of trades and design studies that you could do with these plots. And you can plot all your different constraints on them to help you kind of, okay, we need to have this much power from the fuel cell, this much power from the turbine. So that's exactly what I did for these concepts. So I have these constraints listed here. So the CIT is constrained to 1250 C if applicable. Then I also limited how much air usage the fuel cell could have, as well as fuel usage, because when the percentage of oxygen and hydrogen in the fuel cell gets too low, you can get a significant decrease in performance due to those kind of electrochemical losses I briefly mentioned. And then the goal was to maximize energy density. So I plotted those energy density contour on those constant power lines. And what this maximizing energy density does is it kind of is the best of both worlds of getting really good efficiency as well as pretty good range. Because what it ends up doing is it kind of puts you in this region where you're at close to almost the maximum range of the system, but you're also at pretty high efficiencies as well. So that's what this table is. It's kind of summarizing the results of these size systems when you follow the constraints on the top left. So I'll just kind of highlight some things. Here you can see kind of the takeoff and cruise efficiency that was estimated by this model. And when you compare, what we're getting with this SOFC hybrid system to existing technology, existing battery hybrid is maybe around 30, at best, maybe 40% efficient. And we're right on par with that. Especially with much of the larger scales. And then you can kind of compare the two aircraft, the two single aisle aircraft to the existing LEAP 1B, which is anywhere between like 36 and 40% efficient. And we're seeing a significant increase in efficiency, going up to 55, 67, depending on kind of your pressure ratio, and then even up to close to 70 for kind of this fully electric Boeing 737. So, these systems, when applied to these concepts, they can, give you this step change in efficiency that's going to help you both environmentally and for fuel burn wise. And then lastly, kind of energy density. I'll show that metric here. So the existing UAM concepts that, NASA has published, they're utilizing kind of a turbo generator battery hybrid system. So the energy density of that is shown here with a 1.65. And the reason it's lower than what we're kind of predicting for the UAM concepts is because the batteries are so heavy. So at least that's just how batteries are right now. There is some pretty good improvements in the works, but as it stands now, their energy density is pretty low, just because of how large they need to be. But what you see is that when you apply this SOFC hybrid system to these aircraft, you're able to get energy densities that are better or matching kind of the existing energy densities. So for the full-scale Susan and the fully electric 737. The existing energy density of kind of the LEAP 1B is 4.8 kilowatt hours per kilogram. And we're able to maintain that, pretty much on par if you look in this left column, while, getting close to doubling the efficiency. So that can be very, very beneficial because you kind of maintain the capabilities of the current existing technology, but with that increase in efficiency. All right, so I talked about a lot, went a little bit over, so I'll try to run through this quickly. But I like to give kind of an overall summary of what I've been talking about today. So I started with kind of this motivation of why a more electrified aviation can help you both economically and environmentally. And it's mainly just due to higher efficiency is going to reduce your fuel burn. So it's going to save your costs and it's going to save your carbon emissions. We kind of chose this SOFC combustor gas turbine system as a possible candidate for these, power systems of these more electrified aircraft. But that system has some, unknowns. So that's the reason why we did this whole study with how these fuel cells behave under pressurized conditions. And what we see is, pressure increases fuel cell performance, which is a good thing. But when you're designing these kind of stacks for actual application, you need to be sure that there's not going to be any fuel leakage. Because what we saw is that if there is kind of a crack, or is a fuel leakage path, when you go up in pressure, it just gets worse. So that definitely needs to be considered when you're designing it. And then kind of using that system, using that pressurized data, we dove into the SOFC modeling. So theoretically, these local partial pressures are where the effect of this total pressure increase is happening inside the model. So identifying each of those terms within kind of the loss phenomena and loss kind of equations, the way you get those partial pressures is with your diffusion model. And this diffusion model is where you're considering changes in pressure, changes in gas composition. And, there's complex, shiny models out there, but, some of the better ones was fixed law, because it's just for its simplicity, even compared to, the dusty gas model and those more complex models. Using the modeling and using the diffusion modeling, as well as some of the testing, you can fit the fuel cell you can fit the experimental data to the electrochemical model, and that gives you kind of a tool to explore and learn more about what you tested, where we can estimate that the cathode is likely the dominating source of low potential for the fuel cells that we tested today, or that I discussed today. And then using that kind of more complex electrochemical model, we want to have kind of a rapid performance design evaluation tool. So that's why this SOFC reduced order modeling took place, so that it can feed into kind of modeling the full system in an aircraft. And then kind of the same idea for the mass. You need to be able to capture the mass of this system within the aircraft, and that'll feed into kind of this full system model. And then, when you actually try to size and apply the system to the real deal, to an aircraft, you find that, this system can be pretty good. It can give you a good increase in efficiency, as well as, a good increase in energy density. During my time here, I've been fortunate enough to be able to travel a lot. So that's why you see all these different conference publications. And then a lot of the work I talked about today is in the process of being submitted, or already submitted, or in the process of being submitted to a journal. I'm running pretty short on time. So I'll just say one thing from this future work is that, if the aviation sector might actually be the hardest place for this SOFC hybrid to actually enter the market, because the FAA has so many different regulations. You have to get through so many different approval things. You have to, it's pretty hard. Aviation is maybe the hardest one. So it might be smarter and easier to start at maybe the stationary power market, auxiliary power, locomotive, marine, these other kind of transportation modes that maybe have less stringent restrictions. But, I'd like to acknowledge all the people that helped me. These are the 3 programs that mainly funded me, supported by the DoD, DOE, and NASA. And special thanks to all the students in the lab, and Brian and Tyson as well, being helping so much along the way. All right. Thank you guys for attending, and I'll open for questions.